Alright, this video is going to discuss using multiple batteries in both series and parallel, and a combination of series parallel. Alright, so batteries are actually electrochemical devices. And so the actual voltage that they have, it depends on their chemical makeup. So there's a nominal voltage due to the type of materials, whether it's lithium ion or alkaline battery, and then there's the charge that we put on the battery. So there's also an ampere hour rating, which specifies exactly how much current over a period of time that the battery can put out. So as you can see here with this example, we have a 3600 milliampere hour or 3.6 amp hour battery. So theoretically that means that this battery could put out 1 amp for 3.6 hours, or 3.6 amps for 1 hour constantly. And then of course, along with the voltage rating and the power amp hour rating, that kind of gives us a wattage or total energy that's available, watt hour. Alright, so when we connect up the batteries, we could either connect the batteries up in series connections, or we could connect them in a parallel connection. So if you connect two batteries in series, that means that all the current in the first battery is also going to have to flow through the second battery, right? So remember, the definition of series is that every electron flowing through the first one is also going to have to flow through the next one. It's got no other choice but to move through both batteries. And so when we look then, we can set up so that the polarities match, so that the two batteries are working each other, or we could put them such that the polarities are opposing each other. So let's take a look here. Now again, this assumes ideal conditions in each case here, but one of the things that we do constantly is we look at like charging our cell phones or our other portable devices, and basically what we're doing there is we're taking a DC power source and we're wiring it up to, say, a cell phone or whatever, but we're putting charge from our primary external power source to charge up that phone. So we're actually connecting the positive of our power supply, our external power, to the positive of the cell phone or other device, so that we're putting charge into that battery and storing that charge. Okay, so that would be an opposing sources. Alright, so if we do parallel connections, remember the definition of parallel says that those two devices share both sides have the exact same node. So if we take a second battery here, okay, and that would be a parallel connection. So we have the top node and the bottom node, and we're sharing both of those. So that's a parallel connection. So now when you do this, the matching polarities mean that they're going to share the workload. It's the exact same voltage, but they can share the amount of current. So that if you're, say that you're feeding 1 amp into a resistor, okay, so let's say that we had 10 volt batteries. Each battery was a 10 volt battery, and we had a 10 ohm resistor. Then that would mean that we are going to feed half an ampere from each battery, so that we, Ohm's law tells us that this is a 10 ohm resistor with 10 volts across it. So Ohm's law tells us that it's going to have 1 ampere of current flowing through this. But if we look here at this point, this battery, if the two batteries were ideal batteries of exact same voltage, each of them would be outputting half an amp. So we'd be outputting half an ampere out of each battery. And then at this joint where the two are wired together, then when we look at this current here would be the 1.0 ampere to feed, to satisfy Ohm's law. So they would share the load. Alright, so here's an example. We just, with a single battery, it's pretty much actually kind of what I was showing you here. We have a E1 is a 10 volt battery with a rating of 1 amp hour. So again, theoretically, this battery could put out 1 amp for a constantly for a full hour, and that would then give us the power. It would be giving us 10 watts of power. Okay, so notice it's the 10 ohm resistor I had above, and so we're going to have 10 watt hours. So this battery is outputting 10 watt hours, and the 10 watt hours of energy over here is being converted into, actually a lot of times they use W for work here. So remember that a resistor basically converts that electrical energy into thermal energy. So this would be 10 watt hours. Okay, that would be the energy that we are using here. So we have 10 volts across a 10 ohm resistor, so we're feeding the resistor 1 amp. That gives us 10 watts or 10 watt hours. So now let's take a look and see what happens now when we connect these two batteries in series. All right, so now we've got the two batteries are connected in series, and again, what we're saying here is every electron coming out of the one battery is also going through the other. So every bit of charge flowing through one battery must also flow through the other battery. And so these are in series. Well, now, so if that's true, using Kirchhoff's voltage law, if we start down here at 0 volts, down at ground, at 0 volts, down here at ground, then we go up, and so this is 10 volts here, so it's going to be 20 volts up here at the top. So we got 20 volts divided by 10 ohms gives us 2 amp hours, or excuse me, 2 amperes. All right, so we have a current of 2 amperes, and so we're drawing 2 amps out of these 1 amp hour batteries. So, and again, these are ideal, assuming ideal conditions, this battery could feed 1 amp for an hour. So if we're going to take 2 amps out of it, it's only going to last for half an hour. Alright, so it's only going to last for half an hour. Okay, assuming ideal conditions. But notice here that instead of being at 10 watts like we were for a single source, now we're at, there's 20 volts. 20 volts across this resistor, which means that the power is 2 amperes times 20 volts, which is 40 watts. So up here, if we go back up here and look at this example 1, we only had 10 watts. So here we've got 40 watts. We've got 4 times as much power in that resistor being dissipated and turned into heat, but we're only getting it for half the time, right? So the first example, we were getting it for a full hour. Here we're getting 4 times as much, but only for half the time. And so therefore, notice that each one of these batteries could give you 10 watt-hours of energy, right? Each battery could give us 10 watt-hours of energy. So we've got 2 batteries, so we have a total energy of 20 watt-hours. But that energy is only lasting for half an hour. Okay, and then the batteries would be discharged. Now in this case, we have the 2 resistors are in parallel, and so we only have 10 volts. So there's only 10 volts. There's only 10 volts across this resistor. Okay, remember, if we're going to put this in Blackboard, we need 3 significant digits. But there's 10 volts across the resistor, so the resistor is only using 10 watts, which was like example 1. It's only using 10 watts. It's feeding 1 ampere of current down through the resistor. But if we look over here, if we put an amp meter right here, this is only going to be outputting half an ampere. And this one is only going to be outputting half an ampere. All right? Which means that each one of these batteries, again, remember the rating of these batteries was 10 watt-hours, but we're only taking half an amp out instead of a full. So theoretically, this thing can last for 2 hours. So in this example, we've got 2 batteries. We're using 10 watts, but these 2 batteries will actually last for 2 full hours now. Okay, so by putting in parallel, we've take only half the current out of each one, and therefore they will last. You know, if it's rated for 1 amp for an hour, then if we take out half an amp, it'll be able to continue doing that for a full 2 hours. Again, we're assuming ideal batteries here. But if that's the case, this thing would actually last for 2 hours, and it would be 20 watt-hours. Because remember, each one of these batteries is a 10 watt-hour battery. Okay? So each one of these 2 batteries, and in every example I've done so far, is a 10 watt-hour battery. I've got 2 of them, so that's 20 watt-hours. We're only using 10 watts at a time, so the battery is going to last for 2 hours. Okay, where if we go back and we look at example 2, when they were in parallel, the thing only lasted for half an hour. Right? But it was using 40 watts, not 10 or 20, but a full 40 watts. All right, so now, if we were to combine, thought I had one more example here, but if we were to, say, combine these, here, so that we actually had, like, let me connect these up here. Alright, so if we were like to connect this up like so, now we have 4 batteries. Each battery is 10 amp hours, which means that they would last for 10 ampere. Each battery is 1 amp hour, so that's we got 4 of these, so 4 times 10 watt hours, which would give us 40 watt hours of energy. Okay, so we have 40 watt hours of energy, and And so we still have our 10 ohm resistor over here, but now the power, we actually have 20 volts here. So we're actually going to have 20 volts across here because we have two of these. This is 10 volts and this is 10 volts, and these two here are connected in series. And then this one over here is 10 volts and this one over here is 10 volts, and these two are connected in series. So from ground, down here at ground, up to the top, we actually have 20 volts. Okay, so we're at 20 volts. We're at 20 volts, and so we've got 2 amps, 2 amperes of current flowing through this. So 2 times 20, so we're at 40 watts. Okay, so but each one of these is outputting 1 amp hour, or 1 amp. This battery is outputting 1 amp, and this battery is outputting 1 amp. All right, and so this is in series with the one above it, so it's also at 1 amp. Okay, use my 3 digits here. And this one is at 1 amp. So we have 1 amp over this way and 1 amp coming up here, so they come together, and now we have 2 amps here. So there's 2 amps. As I already said over here, there's 2 amps going into the resistor. So the resistor is dissipating 40 watts. Okay, so this has to be a big resistor. It can't be one of those half-watt resistors we used in lab, or even a 2-watt resistor. It's got to be a really large resistor. But that resistor, if rated at 40 watts, we can do this, and so it's going to have 40 watts through it. And so that's going to be for 1 hour, right? Because this is a 1 amp hour battery. Each one of these is a 1 amp hour battery. So, and they have 1 amp flowing through them. So they're going to be able to keep that up for 1 hour. So 1 hour times 2 amps, okay, times the times the 20 volts gives us 40 watt hours. So, right, we have 4 batteries. Each battery is good for 10 watt hours. So it doesn't matter whether they're connected in series or parallel. It was kind of like the resistors, right? Resistors are using whatever power that resistor is using based on the current through the resistor and the voltage across the resistor. And you just add the powers together. Same thing with your batteries. You can add the power or the energy of the batteries together. It doesn't matter whether they're in parallel or in series. The energy or the power that they supply adds up. Okay, so we have 4 10 watt hour batteries for a total of 40 watt hours, and that's what this resistor is using. It's got 2 amperes flowing through it with 20 volts across it, which means that in an hour it's going to be using 40 watt hours of energy.